Thank you
Okay.
again for the invitation today. I really appreciate being able to join this and to follow on from the two talks that we've just heard. And I think hopefully this is sort of quite complementary to the talk that Mike's just given, in both highlighting the sort of variety of marine and coastal hazards that we have in volcanic island settings. And also linked to both Mike and Erin's talks, the sort of lessons we can take from re-examining historical events and piecing together evidence from those past events to inform future monitoring and mitigation strategies. So I'm going to give a quick sort of talk through volcanic landslides, essentially, but landslides in island settings. And the sort of complexities of those and the hazards they can pose, particularly in terms of tsunami generation. And while extremely large volcanic landslides have received quite a lot of attention, particularly in ocean island settings, um, historical events have been somewhat smaller and mainly in subduction zone settings at arc volcanoes. And there's a lot that we can learn actually from these events, some of which are still quite poorly known. And the image in the background here is of a relatively obscure volcano in Papua New Guinea called Ritter Island, but which actually is a really important event for understanding these types of processes. It's the largest historical volcanic edifice collapse, and it was in an island setting and generated a damaging tsunami that had impacts to several hundred kilometers. And I think this image hopefully gives you sort of a sense of that type of process, in that we can see this was a conical structure, and we've got this sort of unusual shaped island that is the remnant of the amphitheater shaped collapse scar. So I'd sort of suggest that non-seismogenic tsunamis are an important hazard alongside earthquake-generated tsunamis, and perhaps under-recognized in terms of the risk they pose. We can see here from a global compilation, this is over a bit over the past century, we can see various tsunami types, and they're scaled here in terms of their fatalities. And you can see that as well as several yellow stars from earthquakes, we have quite a number really of volcanic and landslide generated events, and they're actually quite clustered in this part of the world, in the sort of Western Pacific, Indonesia, Philippines region. So they are a significant component of tsunami hazards, and often these are challenging and have particularly high impacts because of their short travel times to nearby coastlines, limited warning potential, including no felt earthquake in association with the tsunami, and often extreme local wave amplitudes. Now, this particular region that in the historical data set is evident as a part of the world with high impact from tsunamis. When we look at a global compilation of large volcanic island landslides, and all of these are prehistorical, we can see that there's many events known from detailed studies around the Canary Islands, in the Caribbean, for example, Hawaii and elsewhere. But we can actually see that this zone of the Western Pacific actually represents a real gap. And this is a knowledge gap linked to a lack of really marine studies in this region that have pieced together these past events. And we know from the historical record there are many damaging events in this region, and it's very likely there are prehistorically many other events, including some very large landslides and tsunamis. But overall, what this global compilation shows is that this is a ubiquitous process. These types of events are widespread, and they can have potentially severe impacts. The severity of those impacts are evident if we look at volcanic fatality data sets. So this is a compilation from a few years ago now. But what is notable, I think, is this is a compilation of all volcanic historical volcanic events since 1500, I think, and sort of cumulative fatalities from those by cause. And perhaps unexpectedly, tsunamis are high up that list. Now, as Mike's mentioned, lahars are also high, but we can see that tsunamis account for a very significant proportion of total volcanic fatalities. And this is actually from a small number of events. Most volcanic eruptions do not generate tsunamis, but when that does take place, these can be particularly devastating. So learning from those few historical events is important. This isn't sort of a particularly long list, But these can provide a lot of information for better preparing for future events for this type of low frequency but high impact volcanic hazard. So I'm going to quickly run through some recent work on three events, and in particular focus on the Anak Krakatau tsunami of 2018, and talk through some recent results. And this is work from a wide range of collaborators in the UK, other parts of Europe and elsewhere, including many Indonesian colleagues as well that have worked on these projects. So there is a sort of, Krakatau is an interesting volcano. There's a certain symmetry between, it's obviously well known for its devastating eruption in 1883, and many of the impacts of that eruption were from the associated tsunami. That was a complex tsunami, definitely eruption associated, and probably a distinct mechanism or set of mechanisms to that which occurred in 2018. Which is quite clearly a sort of volcanic landslide tsunami, even though it did occur during eruptive activity. So in December 2018, the image on the right, the volcano was reduced from this form with subaerial activity to submarine activity, as about half that island collapsed into the sea and the vent was cut perhaps a few tens of meters below sea level, and around a quarter of a cubic kilometre of material moved into the ocean and generated a tsunami. So that took place about 135 years after the catastrophic 1883 eruption, during which time this entire island edifice had been built. So this presents a very interesting case study because we have the life cycle of this volcano distilled down into a very short time window. And we can understand the growth of this volcano, its collapse, and actually its regrowth, and think about its future stability as well. So on a sort of relatively small scale, it allows us to really understand volcano structure, volcano construction, and instability, and the tsunami generation arising from that. Now, there are some peculiarities as well for this volcano in that the reason it becomes unstable is closely linked to actually the 1883 eruption and the formation of a collapsed caldera, a subsidence caldera, during that eruption. Now, the same sort of vent region has remained active during the regrowth of Anak Krakatau, and this means that Anak Krakatau is constructed on the edge of that 1883 caldera, which results in some inherent instability because of that unevenness in the basement on which this volcano is constructed. So we can see what the volcano looked like in 2018. We see a satellite radar image of that. And then following that collapse on December the 22nd, what remained was this north eastern half of the island. So we can see about half of the island disappeared into the sea during this collapse. And we think that was a single stage failure, as I say, around a quarter of a cubic kilometre. Now we know that from offshore work, and this was led by colleagues at Southampton, in fact, where we can see the deposits image from this event. So we can see large blocks transported 2 to 3 kilometers into the caldera floor. So this is the floor of the 1883 caldera, which you can see on the top image. And it's this mechanism that generated the tsunami from that event. And we can demonstrate by modeling that as a tsunami source that is compatible with the impacts and the observations. So this demonstrates that this tsunami is entirely consistent with being generated by a collapse of that size as a landslide type source. And this caused severe damage on the shorelines of the Sunda Strait, which you can see here, including over 400 deaths on surrounding coastlines at distances of around 50 kilometers. So we've been interested in sort of thinking, well, why did the volcano collapse when it did? What made it unstable? And as I've mentioned, this can be linked closely to its position on the edge of the caldera, which you can see here. This is now an image of the seafloor with Anak Krakatau perched on the edge of the caldera. And what we've been working on, this is work with a current PhD student, Keris Merridew, is looking back at the archives of Anak Krakatau's growth and its structure to see if we can understand why that became unstable. And there's a rich record actually from historical eruption descriptions and maps that help us reconstruct the structure of this volcano in a fairly unique way. So we can see that up until around 1960, The vent was beneath sea level, and this produced phreatomagmatic eruptions that created a tough cone made from ash deposits. Um, Now, after 1960, the vent became subaerial, and therefore the eruption started producing lava flows, which were then topographically confined by this prior accumulation of material to then build out on the unstable southwest side, which is where the deeper part of the caldera lies. So there's this sort of lithological boundary dictated by its position and the eruption style changing that led to the loading of this southwest side by lavas produced after 1960. And eventually this manifested as the 2018 collapse. Now, looking at all these historical records, we've been working on sort of building up an internal model of the volcano from these types of maps and images. And that has enabled us to generate cross sections to understand the volcano structure. So on the right, we can see a simple sort of boundary between this tuff cone in the pale grey and the lava and pyroclastic cone in the dark grey. And we can sort of use that to understand when the volcano collapsed and then project that towards future growth patterns. So recognizing this inherent sort of northeast southwest discontinuity, we've been able to sort of estimate the volumetric growth on those two sides of the volcano. And that's what you can see here to the northeast and southwest. To understand how that edifice has built up through time with a changing growth rate, and then to use that rate to look at post-collapse regrowth of the volcano and to identify the trajectory that regrowth is following in the future, which is a necessary basis to then think about future stability of this volcano as it continues to grow. So constraining those future trajectories will require ongoing surveying of the volcano as it grows, but this is really valuable now to build on this past work and to understand the future loading of that southwest flank and how failure in the past was linked to the gradient, to the rock properties, and to the growth of the volcano. Now, just to quickly show a couple of other examples, I'm realizing getting a bit short of time. Ritter Island, that first example that I showed you, is an island in Papua New Guinea, and prior to 1888, again, it formed a conical edifice, a bit like Anak Krakatau, and then failed catastrophically into the sea. Now, this was a rather larger event, around 10 times the volume of Anak Krakatau, and we can see some similarities, though, in terms of the nature of the submarine deposit here. And actually, this resulted in very widespread mass flows that moved over 80 kilometers across the seafloor. And the total volume of this event, including the sort of remobilized seafloor sediment, was around 13 cubic kilometers, comparable in total volume to something like the Hunga Tonga eruption volumes that Mike mentioned in his talk. Now, this generated a larger scale tsunami than the Anak Krakatau event. It was damaging and recorded to distances of over 500 kilometers, which demonstrates the potentially sort of destructive potential of these types of event. Now, we think this was linked to gravitational instability of the volcano, potentially occurring over quite a long time period, and coupled to growth of the edifice that eventually resulted in instability and catastrophic failure. But it shows that these types of large-scale edifice failures can occur in a single phase that is efficiently tsunami generating. Now, finally, just in a couple of slides, I want to highlight a sort of ongoing recent project at Ruang volcano in Indonesia. And I just show this map at the start to show that while I've said there are a few historical examples to learn from, when one looks into the records, there are sort of more than you might initially think, particularly quite small volcanic tsunamis, many of which we know very little about. Now, recent attention has been focused on Ruang, which is here in northern Indonesia, because of its eruption in 2024. And we can see in this image of this eruption, pyroclastic density currents entering the ocean down the flanks of this small volcanic island. Now, it's a particularly hazardous setting because of this island where the photo is taken from, called Tagulandang, which is just across a short strait from the island of Ruang. Now, in 1871, another eruption of Ruang, very similar in style, generated a devastating tsunami that killed likely over 400 people on Tagulandang, so similar in that respect to the Anak Krakatau event. Very little's known about this event though, so we've been sort of re-examining these past eruptions of Ruang to try to better understand the 1871 event. And while the eruption itself doesn't look anomalous, it seems there is evidence of a potentially small flank landslide occurring during that event. And that flank landslide was particularly damaging, likely much smaller than Anak Krakatau, but damaging because of the particular setting of Ruang with this nearby settled island. So we've been using sort of reconstructions of Ruang. You can see here sort of recently collected drone model, some new bathymetric surveying, and actually some exposures that were not available before the 2024 eruption, but are now newly revealed because of that activity and that we can learn important lessons from. So I'm just going to finish on this slide. Apologies for sort of going slightly over time. But just to summarise, island volcanoes present a wide variety of marine hazards, as we've seen in these talks. And flank landslides, I think, present a particular challenge. They're not always closely linked to eruptive activity and are challenging to monitor, but they have the potential to generate extreme tsunami magnitudes. And a first order priority I'd suggest is to identify vulnerable sites, such as that at Ruang, and to take key lessons from historical events, which can help constrain future activity. And even relatively small events can have severe consequences depending on their particular setting. These events have limited prospect for real-time warning, so it's important to think of other ways to incorporate these into hazard management planning. So I'll stop there